Okay, we're going to talk about simple harmonic motion. We're going to try to talk about it without a lot of the jargon or the sinusoidal equations that go with it. Not because those things are bad, but just because it's a simpler place to start. Simple harmonic motion means a lot of different things. Let's take a look at some of the things it doesn't mean. Okay, it doesn't just mean back and forth motion. Just because something moves back and forth like a tennis ball against a wall doesn't mean that it's simple harmonic motion. But it could be something back and forth. All simple harmonic motion has something that moves back and forth, side to side, up and down, something like that. So that will be included. Doesn't mean it's periodic. Like I said, the example of tennis ball hitting back and forth on the wall, that is periodic. It's going to come back to your hand if you throw it the same way every time, the same time. But simple harmonic motion is periodic. The thing that makes it different is that it moves back in its periodic motion about an equilibrium point. There's going to be some point in the center that it wants to settle into if it can. If it was allowed to settle, move forever, or if it was allowed to, it would get back to that equilibrium point. That's where it would sit if you didn't move it away from it. And the restoring force is going to increase as you move further from equilibrium. Like the ball against the wall, it doesn't matter how far I am from equilibrium, right? I throw the ball, I have to push against it every time to get it to go against the wall. The ball pushes it back, comes back to my hand. That's not really, there's no equilibrium point in the middle. If I threw it far harder, it would just go further away. And the restoring force, the equilibrium point doesn't matter, doesn't affect the equilibrium point or the force. All that affects the force is my hand. Okay, you can see a good example of that is the spring there with the mass on it. As I move it further away from that resting point, it's going to want to get back to that resting point. So that spring is going to pull harder and harder the further I pull it to the right. The same is true by pushing it to the left. If I compress that spring, it's going to want to push back to the right and get it back to that equilibrium point. That's what makes simple harmonic motion. Okay. Is it simple harmonic motion? Let's look at some examples. Okay. Car moves in a circle. Well, it is periodic, okay, but it doesn't have a restoring force. There isn't some equilibrium point where the car is going to try to get to. It's going to keep moving in that circle. So no, it's not simple harmonic motion. A pendulum moving back and forth. Now this is kind of tricky because technically the force on the pendulum doesn't really change. But what does change is the angle of that force. Okay. It's always trying to get back to that center point, and the force does change. It does become actually stronger, as at least compared to the angle. It makes a different angle, more than a straight up and down angle on the pendulum bob, the little weight at the bottom. So yes, it actually is simple harmonic motion. Now some stuff you can measure when something is simple harmonic motion. Hopefully if you've done any playing with springs and masses, you've seen that. Okay, amplitude's one thing you can measure. Okay, that's the distance from the equilibrium point to the maximum displacement. So from where that spring naturally would be to where however far you moved it away. Okay. The period, that's the time it takes for one complete motion. So it's going to go away from where it was, from one side to the other, and then back to the same side it started from. That's going to be the period of the motion. Another thing we can measure is the frequency. The frequency is the number of complete motions in a given time. So it's if it moves 10 times per second or 20 times per minute, that's the frequency of the motion. So those are three things we're going to talk about measuring during simple harmonic motion. Okay. The units for them, well, they're pretty easy. Amplitude is a distance, so it's going to be measured in meters, centimeters, stuff like that. Periods of time, it's going to be measured in seconds. Frequency is the only one that has a new unit. It's 1 over seconds. Sometimes people say cycles per second, but cycles isn't necessarily a unit, at least not when we measure. 1 over seconds is also called hertz. It's abbreviated Hz. You can see it right there. Now, how do you know a distance that you're given as an amplitude? Okay. It has to be from the center of motion, the equilibrium point, to the edge. That's the only way you get a real amplitude. You can see it in the picture. Okay. You can see that there's a spring there, and they give you a distance like of the spring, and then you add a mass to it from A to B, and then it goes down to a lower point. Okay. Now, the second point is the equilibrium point, because you can see that it's balanced out. Okay. That mg is balanced out there, the force of gravity. Okay. And it goes down. So the amplitude is going to be the difference in height from the bottom of the block to the bottom of the block. Actually, I think that picture is wrong. I was actually going to mark on it, and I'm going to. Okay. It would actually be this distance here. Okay. It'd be from the top of the block to the top of the block. That would be the amplitude. Okay. Now, if you have the whole range of motion, like from the top to the bottom, the amplitude is usually half of that range. So if it's 10 centimeters to get from the bottom to the top, the amplitude is usually 5 centimeters. If it's 10 centimeters to get from the left edge to the right edge, the amplitude will be 5 centimeters. Now, how do you know the time is the period of motion? Again, the period is the time to get from one end to the other and back. So it's the time, if it's a pendulum, to go start on the left edge, swing over to the right edge, and then swing back over to the left edge. That's how you know it's a full period. If it's a time to get from one side to the other or one end to the other, the period's going to be twice that time. If it's a time for two complete motions, to get from one side to the other and back, and then one side to the other and back, the period will be half that time, and so on. So that's how you use any time to come up with what the period was, as long as it describes the actual motion of the object. And how's period related to frequency? Well, you can see from their definitions that they're kind of related. The frequency is the amount of time, is the amount of number of motions in a given time, and the period is the amount of time in a given motion. So they're inverses, which turns out pretty nice. Period is going to be 1 over the frequency, or the frequency is going to be 1 divided by the period. Again, they just work out the same way each time. So if I have a period of 5 seconds, frequency is going to be 1 divided by 5 seconds, or 1/5, 0.2 hertz. It kind of makes sense. If the period's 5 seconds, you're going to go through 0.2, 1/5 of a cycle during that 1 second. That should be how it works. And I don't think I put a slash there, but I'm gonna need a slash there, so it was 1 over period. Okay. So how about forces in simple harmonic motion? We talked about forces already. Okay. Forces always try to move the object back to equilibrium. The spring is going to do that. As we said, that there's one of the qualities of simple harmonic motion is it has a restoring force that tries to move things back to equilibrium. Okay. So here's a spring. You can see that wants to be at x equals 0 because that's the resting place. And then right now it is at x equals a. The equilibrium point is, like I said, x equals 0. Okay. And the spring is pulling it to the left to get it back to equilibrium. So that's going to be the maximum restoring force that you need. Now, if we look at picture B and C, you can see in picture B there, it's actually moving to the left as it goes from right to left. And in picture C, it is all the way to the left. That's the farthest to the left it's going to go. There's no spring force in picture B. The spring is attached, but it's not compressed and it's not stretched. The block is at equilibrium, right? The block isn't, the spring isn't doing anything there. Okay. And when it's all the way over on the left-hand side, the spring is pushing the block to the right. That's the maximum restoring force. It's restoring it. It wants to put it back to that x equals 0 point. So you can see that's where the forces are in simple harmonic motion. Okay. At the maximum amplitude, the spring has the maximum restoring force. In between 0 and x equals -a, it has rightward restoring force. It just has less of it. But when it's at negative A, it has the maximum restoring force. Now, energy and simple harmonic motion are pretty simple to understand also, no pun intended. Okay. When the spring is compressed or stretched, it's going to have some elastic potential energy to it. And if it's moving, it's going to have kinetic energy. So if we look at the pictures, there's the picture from A. We have the block all the way over on the right. It's got the spring really stretched out. Okay. So it's at the maximum amplitude. It's got lots of elastic potential energy. It's not moving, so it has no kinetic energy at point A. But if we take a look at points B and point C, we can see we're going to have different results. At point B, it's not stretched at all. So we're going to have no elastic potential energy at that point. Okay. But you can see there's an arrow. It's going to the left. It's moving pretty fast. So we're going to have lots of kinetic energy. Now let's focus down on the bottom left at point C. When it's all the way over on the left-hand side, it's compressed that spring pretty good. So it should have lots of elastic potential energy. And it's not moving, it's turning around. So it's going to have no kinetic energy. So we can see what kinds of energy it has. In between those points, it has both kinds, and it's just losing one kind and gaining the other, depending on what direction it's moving. As it goes from B to C, it's losing kinetic energy, and it is gaining elastic potential energy. Now, the motion of the object would make a great position time graph. We can look at those and see. There's the first picture. It's at point A, so I'll make a dot for it on our graph. Second picture is at x equals 0. It's a little further in time, so I'll make a dot for that. The third picture is at x equals negative A. It's on the left-hand side. That's going to be below the time axis, so I'll put a dot for that. Now, when it goes back from left to right, I'm going to get dots for that as well. It's going to go back to equilibrium, then all the way over to the right, then back to equilibrium, then all the way over to the left, then back to equilibrium. Well, you get the idea. And if I sketch that out, it's not going to look like a zigzag pattern. It's actually going to look more like a curved line. Okay. It's going to look like a sine wave. I apologize because my line is kind of wavy there. But it's going to look like a sine curve. We're not going to worry about making a sine curve, but we are going to worry about using that shape of the line to describe what happens. Now, if we read that graph, we can actually figure out all those quantities that we were measuring earlier. Okay. So the first thing we're going to do is we're going to measure the amplitude. The amplitude is the distance from equilibrium to the maximum point. Well, we can see that the equilibrium is this line down here. So it's at 0. Okay. And the maximum point is up here at 2. So if I subtract those 2 minus 0, I'm going to get an amplitude of 2 centimeters. The next thing I want to do is I want to find out what the period is. Well, I'm given the time in centimeters, or sorry, time in seconds. So I can just find the time when it gets, and you can see that we have the time when that's at the maximum point. Then it gets to the other point. Then it gets all the way over to here. Okay. Well, at this time, it's time equals 0. This time over here is time equals 3. Well, if you subtract those two, you get a time of 3 seconds. Okay. And we could have picked other points and gotten the exact same result. And again, to find the frequency, we just take the inverse. So it'd be 1 over 3 or 0.33 hertz. Okay. So you can do it with any graph that you want. We're going to try it again with a different kind of graph. This next one is different. Okay, that's a little longer, but I'm not real concerned about that. What I am concerned about is that this time our equilibrium point is in 0. It's kind of a pain. Okay, if you look at it real closely, you can see that it's the point in the middle. I'm going to draw that. It's like right here. Okay. And if you track that, you get an equilibrium point of 0.23 because it's just below that part there. If I measure the distance, this is at 0.28. So from 0.28 to 0.25 or 0.23 gives me 0.05 meters. Okay. I can take my period from anywhere I like, but this time I don't have the comfort of starting like at 0 very well. So I'm just going to pick points that are easy for me. I think this one is at like 2.1. And I looked for a point over here. It looks like it's about at 2.9 almost. So it's at about 2.2. I'm sorry. So this is close to 2.2. And this one here is close to 2.9. So when I subtract them, I got 0.7 seconds. Okay. And then when I take the inverse of that, I get 1 divided by 0.7. It's about 1.4 hertz. I rounded a little there. So I was able to get those values that way. Okay. Now, again, finding restoring force. Now, we said the restoring force happens when the spring is the most stretched out, or the most restoring force happens when the spring is the most stretched out. So that should happen at the ends. Okay. Okay. So you can see that happens at the top end. It also ends at the bottom end. All those points of restoring force. If I wanted to write down the times when those happens, I'd write down 0 seconds, 1.5, 4, but it should be 3. Okay, 4.5, 6, and 7.5 seconds. All of those times are times when the maximum restoring force occurs. Okay. Now, when is there no restoring force? All the times that the graph, the position on the graph is x equals 0. So those would be all the points when it's crossing that time axis. Okay. So I marked all those. Okay. And then again, if I took the time values for each one, I get values like 0.75, 2.25, 3.75. I kept 3, I don't know why. 5.25 and 6.75 seconds. All of those would work. Position, time graph, and energy. If we look at those, again, these work just like the other ones. Okay, the maximum potential energy is where the spring is the most stretched at the ends. You can see we marked all of those. All the points at the end, those would all be the points where it had the maximum, where it's stretched or compressed, I should say. Okay, so you can take the time when any of those happened and call that a time when it had maximum potential energy. Okay. And the kinetic energy is going to be where the slope is greatest. Those sections where it's at the equilibrium point, that's where the slope is greatest. You can see where all those are marked too. And again, we could pick any one of those and write down what the time is at those points. So like one example for the maximum kinetic energy would be if I picked this point right here and I just went down. And I get a little under 0.6 seconds, so maybe 0.55 seconds or something like that. That would be a point where it had the maximum kinetic energy. So I can do that with any time that I choose and find out what it is. So those are the things I wanted you to know about simple harmonic motion.